So we should be able to do calculations like this. A 40 mil sample of 0.1 molar nitrous acid is titrated with 0.2 molar KOH. Calculate the pH at the equivalence point. And we're given Ka for that acid is 4.6 times 10 to the minus 4. So we can start to think about this by just thinking about, well, what's the chemical reaction that's happening here? We're making nitrite ion. And if we do one of those Ba tables, at the beginning we have 40 milliliters of 0.1 molar acid. So that's 4 millimoles of acid. And then how many moles of hydroxide are we adding at the equivalence point? (40 times 0.1). So, what's special about the equivalence point? What does equivalence mean? Equal. What's equal? The same. That's what equal means. But what are the two things that are equal here? Moles of acid and base, right? Equivalence point of a titration, we've added an equal moles of acid to the, or base to the acid, right? So if our initial sample had 4 millimoles of acid, then at the equivalence point we have added 4 millimoles of hydroxide per the definition of the equivalence point. And so these are going to react, and we're going to end up with essentially none of those left. And what's our concentration of NO2 minus? Not concentration, amount of millimoles. 4. So I take 4 millimoles of acid and 4 millimoles of hydroxide, and together they're going to make 4 millimoles of water and 4 millimoles of the NO2 minus. Everybody okay with that? At the equivalence point, we no longer have a solution of a weak acid. The weak acid is neutralized. We have the solution of the conjugate base. So we have to look at it that way. NO2 minus plus water will give us the acid back plus hydroxide. It's all cramped over in the corner. But in our ice table, we have to use molarity. Well, most of the time, and it's safer to just do it that way all the time. So I've got 4 millimoles of NO2. Oops. What's the total volume of this solution? That's what I started with, plus how much potassium hydroxide have I added? 20. Enough to give me 4 millimoles, right? 4 millimoles of hydroxide, and it's 0.2 millimoles per milliliter. So that's 20 milliliters. You can do that calculation other ways as well. So I've got 4 millimoles divided by 60. 0.067 molar. Any questions? What?
She's talking about from Ba to ice.
So,
why did you reverse the reaction?
Because all of my acid has reacted with the hydroxide. And what I've got left is the conjugate base. So now I'm looking at the conjugate base dissociating to form some hydroxide, and that's what's giving me a pH that's different than 7 at the equivalence point. It's a little bit like this exam problem, because when these react, they go all the way to the end, and then we're going to look at it coming back a little bit. All the acid's been neutralized. So what I've got is 4 millimoles per 60 milliliters of nitrite, which is a weak base. And that comes out to be 0.067 molar. Because at the equivalence point and after, for a weak acid, the solution is basic. Because all the acid's been neutralized. So we're saying initially that this is 0 and this is essentially 0. And so a little bit of this will dissociate or react with the water to form a little bit and a little bit of this. And then, can I use Ka here? No, I have to use Kb. Kb is Kw divided by Ka. So 1 times 10 to the minus 14. My husband's sending me pictures of people's dogs. It's not something I need to be seeing. .2 times 10 to the minus 11? So that's Kb, and Kb is equal to x squared over 0.067 minus x. When we solve for x, x is going to give me the hydroxide ion concentration. What do you think? Do you think x is small? Yeah, this 10 to the minus 11 is pretty small, so let's try that. It's going to be the square root of 2.2 times 10 to the minus 11 times 0.067. 1.2 times 10 to the 1, 2, 3, 4, 5, 6. 1.2 times 10 to the minus 6. If you divide that by 0.067, I'd be willing to bet money it's less than 5%. So the log of that gives me the POH, and then I subtract that from 14 to get the pH. Yes. We can't use the Henderson-Hasselbalch equation because the concentration of weak acid and its conjugate base differ by more than a factor of 10. Yeah. You can use that equation before the equivalence point, but not at or after. Anybody else have any questions? (8.08). So a conceptual question. 2 25 milliliter samples of unknown monoprotic weak acids A and B are titrated with 0.1 molar sodium hydroxide solutions. The titration curve for each acid is shown below. Which of the two weak acid solutions is more concentrated, and which of the two weak acids has the larger Ka? Well, first question first. The more concentrated acid, is that going to take more or less sodium hydroxide to titrate? It's going to take more. Which of these, acid A or B, needed a larger volume of sodium hydroxide? A, right? Because here the equivalence point is out here, it's close to 35 milliliters, and here it was less than 25. So acid A must be the more concentrated. Does anybody have any questions about that?
If we knew that one of the acids was stronger, like if one's a strong acid, one's a weak acid, should we base that off of the pH to know which one is stronger?
If one of these was strong and one was weak, well, that's actually what's it's asking us in the second part. Which one's stronger? Which one has a larger Ka?
Oh, okay. So when the pH is different.
So the pH at the equivalence point is different. Here it looks like it's a little over 9, and here it looks like it's maybe under 9. But where's the easiest place to find the Ka on a titration curve? It's called the half-equivalence point. So that's the equivalence point. And then half of that is like somewhere in here. There's the equivalence point for this one. And that's going to be down here somewhere. The pH at the half equivalence point is equal to the pKa for the acid. So this one has a pKa of, looks like close to 6, and this one looks like maybe under 5. So which is the larger? Here's another way to think of it. If we had a strong acid being titrated, what would the pH at the equivalence point be? 7. So the closer the pH at the equivalence point is to 7, the stronger the acid is. Which one of these is closer to 7? B, right? This pH here is closer to 7 than this one. Those are a little bit different too. So this one has the larger Ka.
So a weaker acid will have a larger Ka.
A stronger acid will have a larger Ka.
I thought you said this one was more concentrated.
It is. Concentration and strength are not related.
Inversely related?
No. Because you can have a very low concentration of a strong acid and it's still a strong acid. You can have a high concentration of a weak acid and it's still a weak acid. Now, a high concentration of a weak acid might be more corrosive than a low concentration of a strong acid. But strength is just how much does it ionize. Any other questions about this one? Yes. So this is actually the pKa.
Oh, okay.
And then we get into that whole negative. Oops, not that one. This one.
That's kind of reverse the smaller the pKa, the larger the pKa.
Yeah, because this is going to be 10 to the minus 5-ish, and, closer to 10 to the minus 6. And this is closer to 10 to the minus 5. And 10 to the minus 5 is a larger number than 10 to the minus 6. It's confusing. Yeah.
So, if we were just looking at this, is it because, like, we could tell off the bat that acid A is more concentrated is because it doesn't have such an abrupt curve?
No, we can tell it's more concentrated because where this break comes is at a larger amount of base added. We had to add a lot more sodium hydroxide to reach the equivalence point, and so the concentration has to be higher. Any other? Yes?
So why are you looking at like the half of the equivalence point?
So the half equivalence point, at the half equivalence point, let's see if I can find a slide on that. May regret going here. It's in there somewhere. I found it. So, at the half equivalence point, the pH is equal to the pKa. That's for weak acids. Because at this point, you've neutralized half of the weak acid, so the concentrations of weak acid and its conjugate base are equal, and it's a really great buffer. And in the Henderson-Hasselbalch equation, when those two concentrations are equal, pH is equal to pKa. Well, what about the titration of a weak base with a strong acid? The calculations are going to be very similar. Our pH curve is going to start basic because we're starting with a base, and it will decrease. The pH will decrease as we add acid. At the half equivalence point, the concentration of the base and its conjugate acid are equal. And then we get to the equivalence point, and we have a solution of the conjugate acid. The pH here is going to be slightly acidic. And then down here, we're going to have the acid added, overwhelming everything else in calculating the pH. Up here, we can use this pH equals something at the half equivalence point, but it is equal to the pKa. It's not the pKb. There's a Henderson-Hasselbalch equation. pH is equal to pKa plus the log of the base over the acid. At the half equivalence point, the weak base and the weak acid are equal. Any questions? This is true at the half equivalence point.
So when you say pH equals pKa, that's going on in the background of half equivalence. And that log is just 1.
Right.
That fraction is
Yeah, this fraction becomes 0.
0.
The log of 1 is 0. The fraction here is 1, the log of 1 is 0, and so pH is equal to pKa. That is here when we've added half of the titrant that we need. Conceptual question about the half equivalence point. What is the pH at the half-equivalence point in the titration of a weak base with a strong acid? The pKb of the weak base is 8.75. What did we just get done talking about? The pH at the half equivalence is equal to what? pKa. So it's not 8.75 because that's the pKb. Remember the relationship between pKa and pKb? Yeah, so it should be C. Any questions? Okay, what about a polyprotic acid? Sulfurous acid being titrated with sodium hydroxide. So H2SO3 has 2 ionizable hydrogens. Ka for the first one is 1.6 times 10 to the minus 2. Ka for the second is 6.8 times 10 to the minus 8. When we titrate this, we're going to see a pH curve where we get 2 equivalence points. One for the first hydrogen and one for the second. That is, if these Kas are sufficiently different. If they are very close to each other, it'll just kind of mash together and it won't be distinct.
Would you consider those sufficiently different?
Yes, these are sufficiently different. The volumes needed to reach each equivalence point are identical. To get to the first equivalence point is taking us 25 milliliters. That's to neutralize the first hydrogen. And it's going to take another 25 milliliters to neutralize the second hydrogen. Because guess what? There's exactly as many of these as there are of those because they came together. So consider these 3 titrations. Titrating 25 milliliters of a 0.1 molar monoprotic acid. I'm just going to kind of highlight the things that are different here. This is a monoprotic weak acid. Titrating 25 milliliters of 0.1 molar diprotic weak acid. Or titrating 25 milliliters, that is way too fat, of 0.1 molar strong acid. Which statement is most likely to be true? All 3 titrations have the same initial pH. Is that going to be true? No. Name one reason. Yeah, we got weak acids and strong acids, right? And those 2 weak acids are going to have different Kas. And the one is diprotic and the other is monoprotic. So that one's not correct at all. All 3 titrations have the same pH at their first equivalence point. What is the pH at the equivalence point for a strong acid? 7. What is it for a weak acid? Something above that, right? It's not that. Right? So they can't be the same. And we don't have to get all the details of that. We just need to find enough to show that that one's false. All 3 titrations require the same volume of sodium hydroxide to reach their first equivalence points. Yeah. The volumes and the molarities are the same. And it specifies first equivalence point. So for this diprotic acid, we're just going to titrate the first proton. And so for each of these, we're going to have 2.5 millimoles of hydrogen ions that we're titrating. The pH at the endpoint is going to be different. The pH at the beginning is going to be different. But the amount of sodium hydroxide added is going to be the same. Yeah. If you change, if these molarities were not the same and these were not the same, if something was different, then it would be different. Yep. Yeah. Since the volumes of the acids and their concentrations are the same, they have the same number of moles of hydrogen ions to be titrated for the first one. Now, that diprotic acid, you'd take another amount of that. It would take twice as much total to go to the second equivalence point. So, indicators. We've used indicators, used them in Chem 1A. Phenolphthalein is our favorite, right? Now we're going to learn more about how do they work. So we can monitor a titration with either a pH meter or an indicator. And what we've done up until now is we've used indicators. This next experiment we're going to use pH meters to monitor a titration. When we are using an indicator, we are relying on the point where the indicator changes color to determine the equivalence point. So the end point of the titration is where the indicator changes color. The equivalence point is where an equal number of moles have been added. They are not necessarily exactly the same. If we choose well with our indicator, they will be close enough that we won't care about the difference. But the end point and the equivalence point are slightly different. They're definitely different in concept. So an indicator is a weak acid. It's a weak organic acid that is different in color than its conjugate base. And these substances have very intense color, so we only need a little tiny bit of this indicator to color the whole solution. So when we've used phenolphthalein, we've used either 0.1% phenolphthalein or 1% phenolphthalein, and then we've used like 2 drops of that solution in maybe 20-30 milliliters. So the amount of phenolphthalein that's actually in your flask is very, very small. It's small enough that it's not going to affect the titration. It's not going to affect how much sodium hydroxide we add. So this is phenolphthalein. That's kind of a big old mess, right? So when it's in this form as an acid, it's colorless, but if we add sodium hydroxide, get it into a basic environment where we take these 2 hydrogens off, I don't know why well, I guess it's because it moves around like that. It does a whole bunch of rearranging. Then it turns pink. And this is showing the color of it at different pHs. There's 4 and 6. And at pH 8, we're getting this faint pink color. And if we go farther to 10 and to 12, it gets more intense because more of the phenolphthalein is changed into the pink form. So what kind of acids do you remember titrating in Chem 1A? Acetic acid, we titrated vinegar. Tartaric acid, citric acid. We used KHP and oxalic acid as our standardization acids. Are any of those strong acids? No. They're all weak acids. What's the pH at the equivalence point of a weak acid? Above 7. So we get above 7 into 8 and higher, and the phenolphthalein changes color for us. Indicators will change color within a range of 2 pH units centered on the Ka for that indicator. And that has to do with kind of with the buffer relationship here. If the pH is at the pKa, then we'll have an intermediate color. If it is 1 unit above, we'll have the color of the basic form. If it's 1 unit below the pKa, we'll have the color of the acid form. So this is methyl red, and it has a pKa of, doesn't say. I don't know. But this is showing how the color changes in different pHs. Here's pH 2, 4, 5, 7, 9, and 10. So what color is the basic form of methyl red? Yellow. This is probably all the basic form. And what color is the acidic form? Red. So it changes from red to yellow. There's a whole bunch of different indicators. Some of them have some kind of funny names. One of the funniest names, I think, is Eriochrome black tea. I don't know where that came from. Crystal violet sounds fun. Thymol blue actually is a diprotic, and so it has 2, and alizarin also has that. But here's our friend phenolphthalein. And so phenolphthalein will start to see color changes, in the 8 range. So when you choose an indicator, you want to choose an indicator that's going to have a color change. If you're titrating an acid, a color change at the lower end that is close to the pH at your equivalence point. So some of these, like these guys down here, are not going to be useful for titrating acids because they're going to change color. They'll be in their basic form before you even start titrating. So that won't work at all.